Now let's take a look at 1.2, requesting a reward. There's lots of definitions in here that you need to be familiar with. Some of them we've talked about, others we have not. So first of all, let's talk about this term, exponential form. Right, so if something is in exponential form, that is a way to write a number. That's all exponential form is. And there are different parts of an exponential form. So I'm going to, if you look at it this way, you would have, for example, a to the x power, where a is representative of what's called your base. So a is your base, and then the x represents what's called your exponent. Your x tells your base how many times to multiply it to itself. So for example, using the example that they have here, if you have something like 2 to the 5th power, that 5 says multiply the base by itself 5 times. Whoops, I wrote the number 3. Okay, so then that is another way to write 2 to the 5th. And we could also multiply those out, 2 times 2 times 2 times 2 times 2, which would also be another way to write 2 to the 5th as 32. Now, you would have those two things are called, this is called standard form, and then the other one right here, that's called expanded form, because exponential form, that is what this is. That's exponential form. Okay, so we're going to have to write things in expanded form and standard form, exponential form, and then down here we're going to talk now about scientific notation. So pause it, get this into your notes, do what you need to do there. Then the next portion of the text kind of talks about when you put really large or really small values in your calculator. Some calculators display it like this with an E there. Some calculators display it like this with a 10. So we are going to be using a 10 when we write it down on paper. Just know that if you're punching these into your calculator and there's an E, that means the same thing, means of an exponent. Okay, it talks about 12 exponents. Okay, so this is an example of a number that's in scientific notation. Right, so scientific notation, and I'll give you the form of it, is going to be, you would have your base times 10 to some exponent. So this is scientific notation. Write that down, identify that as scientific notation, where this is your base again, the A is your base, 10 is always a 10, and we'll talk about that, but then x is your exponent. That tells you how many times to multiply 10 by itself. Okay, so if you look at what that times 10 to the 12th is doing, that's saying, hey, take this number and multiply it by 10. This is 1 trillion. So you can see how it's a lot easier just to write 10 to the 12th as opposed to 1 with 3, 6, 9, 12 zeros after it. Much easier just to write 10 to the 12th. Okay? Now here's another thing you have to remember. When you multiply by 10, you just move the decimal. So if I'm multiplying 10 to the 12th, that just tells me that I'm going to be moving the decimal over to the right 12 places. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I would have 3 zeros in there, which is where those 3 zeros come from. Okay, so this means move the decimal to the right. Okay, so that's for really big numbers. So make sure you have examples of scientific notation. You have the basic formula for scientific notation or the expression for scientific notation in your notes. Now this last part is extremely important. When you're writing a number in scientific notation, like this number up here, the 1.099511628, that number right here needs to be between 1 and 10. This is between 1 and 10. That's what this statement is saying. So make sure you get this down. It's saying this A number, when I write this out, remember this was my A times 10 to some power. This A value needs to be a number between 1 and 10, and we're going to talk about that. Let's take a look at this problem here. So one day in the ancient kingdom of Monterrec, a peasant saved the life of the king's daughter. The king was so grateful, told the peasant could have any reward she desired. The peasant, the kingdom's chess champion, made an unusual request. So here's her request. She's essentially saying, take a chessboard. All right, and let's say pennies is a ruble. She says, put 1 penny on the first square, put 2 pennies on the second pair, 4 pennies on the third square, and so forth. So you're doubling what was on the square before it, right? So this has 1, 2, 4, 8, 16, 32. So far that 1, 2, 3, 4, 6 only has 32 pennies. And so the king says, hey, rubas, which are like pennies, they're not valuable. Are you sure there's not something else that you want? Because this isn't good enough for the person that saved my daughter. And the really smart person says, no, this is what I want. And he agrees to it. All right, so we're trying to figure out, if he agrees to this, exactly what did he agree to? Okay, we're going to find out that maybe he did not make such a good decision. So in part A, let's go ahead and make a table. And there is a lab sheet that might help you out with this. If it doesn't, you don't have to. But let's take a look at that lab sheet to see if it'll help. Yes, so here's our lab sheet. And also, it gives you the table here. So go ahead and fill that out. And in fact, do of all of A, it says make a table, look for a pattern. And it says for the first 5, but go ahead and fill out the first 10 because part B says to fill out the first 10. Go ahead and do part A, 1 and 2, and then come back. Okay, when we fill out the table, it should look something like this. And then on number 2, part 2, it says look for a pattern. Use your observation to extend your table to show the number of bouts. So we did that already. And then part B, number 1, it says to graph the data. So on B, 1, 2, and 3, we can go ahead and do that. But let's look at the patterns here. You notice, just like what we've seen before, this is not an additive change, it is a multiplicative change. So you are multiplying by 2 every single time. And so this 2 in an exponent ends up being what we now know as your base. Right? So we know that the equation of this is going to be 2 to something. Right? It might be a little different than that too. But it's going to be 2 to something. Now go ahead and try part B, 1, 2, and 3. And for your graph, use a graph that looks like this. Use those intervals for your square number, and then on the left side, that's your number of rupas. So if we look at the graph, it looks something like this. As you move to the right, the graph grows incredibly fast. Right, about 1, 2, 3, 4, 5, 6 doesn't grow that fast. 6 to 7 a little bit faster, but then from there it just takes off, grows a lot faster. Okay, so that is an exponential graph. So part 1, we graphed it. Make sure you describe the relationship that y does not grow at the same rate. It actually grows a lot faster. As x goes up 1, y goes up way faster. And then on number 2, what does the growth pattern show, or how does the growth pattern show up in the graph and the equation? Well, looking at this, like we said, it was an exponential equation. And the growth pattern, since it's multiplicative over here on the table, this represents our base. And then on part 2, how does the growth pattern show up in the graph and the equation? Well, I guess we talked about that already. But number 3, is the relationship linear? Remember, for linear, I should be able to draw a straight line through all of these points. So no, it is not linear for that reason. So that would be your explanation. You can't draw a straight line through it, therefore it's not linear. On part C, it says suppose Chen could make 20 cuts. Right, so now we're back to the number of ballots. Suppose he could make 20 cuts. How many ballots would he have? How many ballots would he have if he could make 40, and so forth? Go ahead and answer those questions and then come back to the video to see how you did. Wait, I just realized I'm reading the wrong one. Sorry. Looking at the wrong, it's like, that doesn't make sense. That's B, number 2. That's what we did. How does the pattern of change you observe in the table show up in graph? That's what we answered. That's why it didn't make sense. And then, what is the equation? We didn't talk about the equation yet, so let's talk about that. Right? So if we go back to the table, we have to find the equation that fits this pattern. All right, so let's say that we have to define our variables. So let's say this right here, the square number represents, let's use S, square number. And the number of rubas is represented by R. Okay, so the number of rubas, since that is your one that depends on the square, right? So how many rubas you get really depends on what square you're on. That's going to be our dependent variable, so we're going to put it first. So it'll be R is equal to, and we know that is going to be 2 to something. So if you look at this, if we're on square 1, okay, then we should have 1 ruba, but 2 to the first is not equal to 1. If we're on square 2, then 2 to the second should be equal to 2. If we're on square 3, 2 to the third should be 4, but that's not working out, right? So actually there's two different ways to think about this. Probably the easiest way is, well, you could just subtract 1. So it's the square that you're on minus 1. So this is going to be our equation, and you can test that. So if we test it, so let's test the 6, no, let's do an easier one. Let's do the 4th square. So 2 to the 4 minus 1, that's 2 to the 3rd, and I know that that's 8, and yeah, I have 8 rubas on that square. So this checks out. That is one of the equations you could have. You could also, if some of you came up with one, this one works as well. 1/2 2 to the S. That works as well. Most people aren't going to come up with that, but just in case you did, I wanted you to know that you're okay, that works. But again, test it. Test some of these values in there to make sure they equal those values there. Okay, then on C, it says which square will have 2 to the 30 rubas? Explain. What is the first square on which the king will place at least 1 million rubas? And how many rubas will be on that square? Lewis uses calculator to compute the number of rubas on a square when it's the first time it's displayed in scientific notation. So C, this is going to depend on your calculator. Okay, so I mean, I can kind of talk about that, but if your calculator has more digits, then it's going to take longer. Okay, so we can't really answer that question, but you can answer it until on your calculator, just keep going up and up, go 2 to the 4th, 2 to the 5th, 2 to the 6th, until finally it turns it into a scientific notation problem. Go ahead and do C, and then come back to the problem, see how you did. Okay, on number 1, which square will have 2 to the 30th rubies? And in this case, if we want it to be 2 to the 31, remember the number of rubas, is equal to 2 to the S minus 1. Okay, and this is representative square. We want S minus 1, we want that to be 30. So what number minus 1 gives us 30? 31. So you will be on the 31st square when you have this expression. And then on 2, what is the first square on which the king will place at least 1 million rubas? Okay. And how many rubas will be on this square? So you're looking for when that would be 1 million. There's multiple ways you could have done this. You could continue in your calculator until you hit 1 million, and this is what 1 million looks like. All right, any calculator can have that, and you want to go until you get 1 million, and actually this is square 21. And so if you do 2 to the 21 minus 1, that'd be 20th. So 2 to the 20th, you actually get 1,048,000 and was it 571 or 76. So on the 21st square, again, I know this is 20, but remember that's the square minus 1, the number square minus 1, that's at your exponent, that's where that 20 came from. And so that's the first square where you hit 1 million. And then 3, Larissa uses a calculator to compute the number of rubas. So that, again, entirely depends on your calculator and what it can display. But right around 2 to the 20th, 2 to the 21st, I mean, it's going to get bigger faster. So it really just depends on your calculator. So let's jump to D, compare the growth pattern to the growth pattern in problem 1.1. And looking at the two, if you look at the graphs side by side, they look almost identical. The growth patterns are the same. You know, even though they might start at a different value, I forget if they started at, like in this case, it started at 1, then went to 2, then 4. I don't remember if problem 1.1 did that or not. But the growth patterns, since they're both exponential, the growth patterns are the same. Now, that is it for the Peasant's Plan, requesting a reward.